Fast-moving topic. So fast that I've got a list of things that I was supposed to say that are in my slides. Remind me to fill them out. I'm going to take a little bit different look at this question of persistent memory over fabrics. And by the way, I've started using the expression remote persistent memory because RPM sounds a heck of a lot sexier than PM over F. Anyway, you'll hear me talk about this as remote persistent memory. That's the expression that I've been using lately. A little bit different take on it than the one that Andy gave, which was mostly focused on persistent memory local, and then Tom's was sort of the mechanics of how you extend it over a wire. I wanted to look at it a little bit differently and start by making really 3 or 4 assertions here, and we'll kind of test those as time goes on. The first one is remote persistent memory is something different. Okay, I think we can probably all agree with that, assert that. It might prove to be a transformative technology, might be. So this is that Gartner, hype curve thing that Bill Magro mentioned this morning, somewhere from, the heights of excitement to the depths of despair back to some, reality of what it's really going to be worth. We're somewhere in that range, but I don't exactly know where at the moment, but we'll figure it out. But there's a lot of hype about it right now. It's unlikely to take the industry by storm. I think a lot of us hoped or thought or believed or whatever that this thing was going to emerge and everything was going to change. That was kind of the heights of euphoria stage. I don't think it's likely to take the industry by storm, but I do think it is likely to gain a lot of groundswell as time goes on and a lot of currency. But we'll see. It's another assertion. This one I know for sure. It's going to take some work to get this done. So the objective for today is really to establish kind of the groundwork or the basis, if you will, for a broader discussion about persistent memory or remote persistent memory. And those who were gracious enough to participate in last night's think tank on this subject, you're the first ones in the pool there. That was the purpose behind that think tank, was to help us begin this process of establishing a discussion about remote persistent memory, and in particular, how remote persistent memory is used. So there's a lot of work that's already been done on remote persistent memory for high availability. A lot of what Andy talked about was the underpinnings behind that. The RDMA extensions to it kind of have underneath them this idea that we want to be able to do replication. So there's a lot of talk about flushing caches into remote persistent memory. But there may be some other use cases out there yet, which we haven't really explored in any great detail. They're not as well defined. And the question immediately arises, I wonder why not? Why haven't we gotten to those use cases yet? And there's this chicken or egg problem here. You got application developers who really want to write better applications, and you got technologists who want to develop better technology, but they're staring at each other going, you first. So in the typical sort of OpenFabrics way, we're going to try to take an application-centric view here. We're going to try to drive this by looking at what the use cases might be beyond the high availability use cases pretty well defined already. See if we can't define some further use cases and understand what that's going to mean in terms of the technology, and then try to reflect those use cases in a set of requirements which will be used to drive APIs, which hopefully will encourage 2 things: the development of fabrics that will support this better than current fabrics do, or extensions to current fabrics, and it will encourage application developers to start move ahead. So I just hit the first thing on my list, which was application centricity. I was supposed to talk about that. This is really sort of a key idea. It's sort of what's driving the OFA these days. We are really starting at the top and looking at what the consumer demands, what's required to make something successful, and then developing the software stack underneath that, rather than start with a software stack, give it an API, and pitch it over the wall and say, developers, go ahead and write your code to it. Application centricity. And that was mentioned a number of times this morning. It's kind of a key point. Okay, one thing I wanted to be clear on is this notion about, did I miss a slide? I sure did. Scope. So if we're going to be talking about remote persistent memory, let's put some scope on it. Obviously, locality is important. So in this room here, when we're talking about RPM, it's remote. So we're not talking about local. Andy's got that covered. The local part's well understood. We're good there. That's why the local part is crossed out, not because it doesn't need attention, but because it's not our focus today. The access method. Persistent memory as a target of memory operations, hence the expression memory, as distinct from accessing a piece of remote storage. There's a real tendency to want to think about remote persistent memory in terms of existing block storage paradigms. My fear is if you do that, what you get is a faster block storage paradigm, which is a good thing unto itself, but really not where we're focused here. We're really focused on accessing this exactly as Andy described it much more succinctly than I could have, being able to peep into memory and read and write that memory location without doing some sort of a page cache or a prefetch operation. So there's access method, that's part 2 in the scope. Part 3, the implementation. And I want to distinguish the implementation of remote persistent memory from the way that the memory is actually implemented. So you could actually build a viable remote persistent memory system on top of a NAND flash-based architecture. Doesn't necessarily require that the underlying device be a byte addressable device. That's one option. But I want to make this distinction between how it is we're accessing this remote persistent memory and how it's implemented. They're different things. Let's not get wrapped around the axle about that. So I hear a lot of people talking about, well, I could do this using NVMe. Well, NVMe is an access method. It's not an implementation. It implies a block level implementation on the other end, but it's a different thing. All right, so that's kind of the ground rules that I'd like to use going forward here. So a little note at the bottom, the distinction between access and implementation is kind of important. What do I mean by access method, storage versus memory? I've used this slide before. I don't need to spend a whole lot of time on it. Presumably everyone in this room really gets it. But you know, a memory operation really is a read or write of a memory location, sort of on a byte-wise basis, and distinguish that from an I/O operation where the data that's being referred to is referred to by some kind of an abstract identifier like a logical block address, for example. You use some kind of storage stack to get to it. The data is transferred between memory and some storage device somewhere. That's distinct from the memory operation where you're not accessing a storage device, you're accessing memory. Just happens to be at the far end of a wire. So I'm going to ask that we can agree that persistent memory refers to accesses to a non-volatile memory device using memory semantics. I liked Andy's definition much better, but this will do for now. All right, those are sort of the ground rules and sort of the context. Let me talk next about what a system model might look like and a little bit of discussion about memory models on top of that. I'm going to wave an example application at you just to sort of convince ourselves that there really is reason for going ahead and spending time on this. We'll talk a little bit about some of the factors that are going to influence us when we start thinking about what the use cases are and how those are likely to impact the implementation of a fabric underneath it. And then we're going to talk about what's next. So general system model, just to get all on the same page here. There shouldn't be any big surprises here. But in the case that I'm thinking of here, it's a local network of some limited diameter. We're not talking WANs here necessarily. I suppose you could extend it to WANs, but for our purposes here, let's keep it to a local network, like a data center or an HPC system or a cluster, something like that, populated by a bunch of CPU nodes providing compute capacity, and then a whole bunch of these, what I would call service nodes underneath, one or more of them. So there's a scale-out thing going on here. You could have multiple of these service nodes to prevent an incast problem if one were to arise. Then I've also got a little picture of what might be inside one of those service nodes. Of course, there's lots of other ways to implement this than what I've shown. This is just sort of to give us all a context in which to talk. As far as the memory model goes, I think the way to think about this is that this remote persistent memory is organized as a pool. And then what happens is pieces of that pool are allocated to particular applications or pieces of applications for their use. So it can be configured as what I would call a flat address space or as an object store. So now I get to cross off another one on my list. Andy was talking about a pointer to 6 terabytes. That's the flat memory model there that I'm talking about. It's just what you see beneath you is just a whole bunch of memory, and you can access it as you do any other memory. So I could cross that one off my list here. Hang on. Okay, doing good so far. So here's an example of why we might want to look into something like this. It's not a very well thought out example and not very rich in detail. It's something that my company's been kind of messing around with some. And it's sort of to convince ourselves that there's reason to pursue this a little bit further. And it's remote persistent memory for graph analytics. And we started out with a couple of questions, why would you want to do something like this? There were a couple of obvious answers. One was, excuse me, it allows you to operate on larger graphs than you could in local memory. This is what I would describe as a scale-up problem, where whatever you wanted to do originally with your in-memory database, for example, did not fit into local memory. And what you were really interested in the persistent memory was for its capacity characteristics. You want to be able to solve a petabyte-sized graph in a smaller number of nodes, and you can do that if you don't have the graph distributed all throughout the network, if you have it centralized in one place in this central remote store. Persist data structures between program execution. There's a reason to believe, inklings to believe, that if you read the data structure in once and then you can execute on it multiple times, that a significant percentage of the time that's spent in graph applications today is refetching that and rebuilding that data store each time. So the idea is here you do it once, you don't have to do it a whole bunch of times, and it persists between applications. Let's see, use existing programming models and languages. That's sort of self-evident, I think. Make better use of available DRAM for algorithms, not just for holding data. I hadn't thought about this one until someone mentioned it to me, but yeah, if you're not using your DRAM for things like holding the data set, you can use it for something else. What that something else is, I don't know. There's some alternatives here, which I'm not going to bother to go through because I'm not expert enough to speak to any of them, but they basically are, this is the way it's done today. So we believe that there probably is a reason for pursuing remote persistent memory, at least for a graph analytics kind of application. And here's an experiment that was done inside Cray. We looked at an intrusion detection system. The way intrusion detection works is you gather a whole bunch of net flow data and you use that to identify what you think is an intrusion. And then what you're doing is you're looking for a similar pattern across a whole bunch of other net flows to see if you can find it elsewhere. And it was sort of a natural application for remote persistent memory. If you're saving all of these net flows in a in a remote persistent memory store and then acting on them. So we thought that there was real benefit in doing that. And in fact, I won't show you any of the performance results because I'm not qualified to speak to them, but they are available today, where we saw that, yeah, even for a very primitive example, there was some speed up to be had in a case like this. So again, further reason to believe that we're on sort of the right track here. There are a bunch more application targets that I've sort of thought of in my crazy little brain. Scale-up databases is one of them. I talked about that just a second ago. That's where what you're really interested in is the capacity characteristic of persistent memory as opposed to its persistence characteristic. It has both of those characteristics. Scale-out or distributed databases. In the conversation at the think tank last night, there was some reason to believe that this one may not be viable, remains to be seen. But this is one where rather than have a whole bunch of instances of an application, each of them with their own little piece of the data set, that there is a large data set and then each instance of the distributed database is accessing that same data set. You got to watch out for encast problems, but we think those are probably overcomable. Graph analytics, I already mentioned that. An HPC application, something near and dear to Cray's heart. There's a SHMEM model that we're talking about, which will be introduced into the Open SHMEM community pretty soon, that allows you to replace certain pieces of the heap with remote persistent memory, presumably to some benefit or gain in performance or resilience. Okay, some key factors that you need to think about, or at least I hope that we'll begin thinking about as we begin asking ourselves what the use cases for remote persistent memory are, kind of in no particular order. But one of them is the target application, or stated differently, what's the characteristic workload look like? If it's a sequential workload, that's one thing. If it's a sort of a byte level workload, that's another. Those are things we're going to want to talk about. So talk about target applications. I already mentioned three of them: analytics, HPC, and database. System objectives. Why are you building the system the way that you are? Are you interested in scale out, for example, or is it a scale up kind of a thing? That's going to say something about how you're planning to use the remote persistent memory. If it's a scale out kind of thing, then you need to talk about how you're going to share that remote persistent memory and how you're going to share access to it. And there's a whole lot of allocation questions that go along with that, and how data is allocated to this distributed application at launch time and so on. Those factors are going to be different if you're doing something that's scale up, where in that case all you're doing is carving out a chunk of this persistent memory, giving it to the scale-up application. So that's going to be a factor to consider. Resource allocation, I just mentioned that. Is it done at job launch time? Is it done at runtime? How exactly is it done? And on what basis and what granularity? How is this sharing enforced and so on? Programming environment, I already talked a little bit about that. I guess I failed to mention the intrusion detection scheme that we were messing around with was based on Python, which was a kind of attractive way to look at it. SHMEM, I've already mentioned that, Java, and there are some other programming environments that we should look at. And these may impact, at the end of the day, what the wire protocol looks like. Don't know if it will or not, but it's things that we should be talking about when we try to characterize use cases. NVM device implementation. I waved my hand at this one earlier. You could build an NVM target device if you chose out of a block-based device, like an SSD or a NAND flash, or you could build it out of a byte addressable persistent memory device. And last on my list was the memory model. I already referred to the flat memory model, which is sort of the one that's familiar to most people. But we also need to be talking about object-based models or object stores, something that seems to be coming up in conversation a lot lately. And if it turns out what we're doing is building an object store on top of a persistent memory device, we want to talk about what the wire semantics are to access an object store, and are they different or not from accessing a flat memory model. So factors that may or may not have an impact on API and fabric design. My role is in the OFA, so I'm interested in APIs and fabric design in particular. But just in the spirit of more broadly, considering the role of remote persistent memory, we should talk about all these factors going forward. And there was something on my list here. Nope, guess not. Okay. So some key factors we should look at. Let me talk just for a moment about this device implementation question. I mentioned this just a second ago. You could imagine building a target device using either byte addressable, NAND flash, or NVDIMM, or some variation thereof. There's lots of ways to do it. Regardless of the technology on which the remote persistent memory is implemented, it's still being accessed as a memory device, not as a storage device. I'm just trying to hammer that point home. This technology choice is going to turn out to be driven by the application access patterns and by economics. So for example, for some database applications right now that do sequential accesses, it's possible to imagine building a remote persistent memory device on top of a block storage type of architecture, take advantage of the economies of scale, and go forward from there. So you shouldn't assume that it's always going to be a byte. Oops, sorry, wrong button. Now I don't have to go through those slides. You've seen them already. You shouldn't assume that it's always going to be a byte addressable device, but it often will be. Pros and cons, for byte addressable, relatively expensive but very big capacity. NAND flash, existing analytics frameworks that stream data are sort of a natural fit for that. The economies of a flash device are very attractive in an environment like that. And NVDIMM, we know where that stands. It's fairly expensive and it's capacity limited compared to a persistent memory device. Okay, flat memory. I've been yapping about this a little bit. Let me just put a little bit behind that so you kind of get the flow of where I'm going with this. There's this idea, this is where we are today. The way this picture is drawn is it's shown both a flat memory device and a object store device hosted on the same node. That's not necessarily the case. I wasn't trying to make the point that you should be able to do both on the same device, just to make the point that there are two different models, the flat memory model and the object store model, and they may have different implications for how they're accessed from the fabric. And this is the exact same thing, just emphasizing the object side instead of the flat memory side. So you can see that there's this notion of an object here, presented application object. So there's this notion of an application object and a memory object, and they're sort of different things, different tiers in the hierarchy, and they're accessed in different ways. So I won't go any further into the object store than that. Hopefully it'll come up in discussion later. All right, I think I've probably already said everything I need to say about this slide. Flat memory, simple, well-understood memory model. Object store is going to give us lots of advantages. I think people really understand that. This isn't a talk about object store, so I won't spend a lot of time here. How am I doing for time? Pretty good. There are implications for the way that the target device is built. If you're doing a flat memory device, then there's obvious emphasis here on the NIC being able to directly access that persistent memory. So it really looks just like an extension of memory, and that the controller, such as it is up here, is really just a supervisory kind of a mode. And in that case, the API is going to wind up exporting memory semantics, which is what both OFI and verbs do today, with either RMA in OFI terms or RDMA in InfiniBand terms. In the case of the object store, the target looks a little bit different. There may still be a path from the NIC into persistent memory, but in general, you're doing sort of higher level functions that are implemented by some kind of a server on the target device. And what may be exported to the consumer in this case is something related to objects as opposed to memory references. This remains to be explored. I'm not, stating this, postulating it, just suggesting that these are the sort of things we should be looking at. Okay, and system objectives, of course, is a big feature having to do with how you're going to implement this thing, what you're trying to accomplish with it. I mentioned this before. You could be building a scale-out system, in which case you're going to be talking about what I call shared remote persistent memory, so you need sharing semantics built into it. If it's a scale-up system, then really it's just a memory allocation kind of a problem. There's disaggregation and independent scaling of memory and compute. This is one that's fascinated me for years. We did storage disaggregation a long time ago, so we took storage away from the compute node. So now there's just a compute node, which consists of a pool of threads and a pool of memory. What happens if we're able to actually disaggregate the pool of memory as well? This is kind of the euphoria stage of remote persistent memory. What happens when you fully disaggregate a server? So we'll see. Okay, use cases, I'm not going to go through these. I've done these in a couple of other forums because we're getting a little bit low on time. Fundamentally, this was an illustration of the use case for high availability as it exists today. This is a use case for what I called remote persistent memory as opposed to remote shared persistent memory. So this is the scale-up model I talked about, where what you're really doing is taking advantage of the capacity of the persistent memory. So chunks of that memory are allocated to two different applications or users or consumers. And it has a certain set of semantics associated with it on the wire. The scale-out case here, this is where there's sort of shared persistent memory, where you have a couple of cooperating, if you will, instances of an application sharing a particular data set. So the distributed database would be a good example of that. Factors affecting the API or network. So I've already mentioned these. Object store is one of them. Flat memory is another. The underlying technology may turn out to be another. How data is allocated is yet another. And there was one more in my list. Nope, can't find it. Okay. So these are things that I think we're going to want to explore as we start talking about what the use cases for remote persistent memory actually look like. Steps forward, there's a lot to think about here. So remote PM for high availability has already been discussed pretty extensively. That's well on its way. But we need to get beyond just talking about the HA use case. So I'm suggesting that we begin by understanding the relevant use cases. This is, again, the mantra, application-centric, drive it from the application down. Even though those use cases don't yet exist. We're going to make them up as we go along. There's that chicken and that egg thing going on here. Understand the access patterns that come about because of those use cases and the value propositions associated with them, and then develop the necessary APIs to meet those needs. So how do we drive this adoption of RPM? I'm getting to the very end here. It's going to require two things. One is what SNIA calls programming models, which is a common understanding among application developers of the behaviors that you should use to access this persistent memory in a reliable way. Beyond the model like that, you need a reliable way to do that, and that would be the APIs that underlie that programming model. SNIA is really good at doing things like programming models, and the OFA is really good at doing things like defining APIs. This is a case where the sum is much greater than the, let's see, how's that go? that the sum is much greater than the parts. Is that how it is? So this is going to take some serious effort on the part of both organizations. And I saw that Andy stole my slide, but that's okay. This is this new collaboration that just emerged. It was just approved in the OFA's board last week. It was approved by SNIA a couple of weeks ago. We've agreed that we're going to cooperate here to do this. And what we're going to do is we're going to cooperate by looking first at developing RPM use cases, if you will. And out of that should come from SNIA a set of white papers describing the relevant programming models related to those use cases. From those use cases comes a set of requirements. And if you've been part of OFIWIG in the past, you know that we're rabid about being driven by requirements. So we're looking for a set of requirements to emerge from these use cases that will be used to drive API development from there. And from that, in OFI land, we expect to develop open source frameworks and APIs, and we hope that vendors will develop network solutions based on those frameworks and the implementation of those APIs. That's how we see this collaboration happening going forward. And that's all I can think of to say. As part of this collaboration, I would encourage you to take a look at the OpenFabrics website, get in touch with either myself or Sean in the back there. We're co-chairs for OFIWIG, which is the OpenFabrics Interfaces Working Group, which is where this collaboration is probably going to start in the OFA side. At some point, we'll pull in the verbs as well. It's not an OFI thing only. It's an OFA thing, hosted at the moment in OFIWIG. Any questions? Do I have time for a question or two? I got time for one. I'll take it. Anybody? Bob, there's a microphone. Hit it.
So you make a distinction between storage, block devices, and memory. And so we've got a good use case for you, but we basically want to create our data sets using standard file-based file systems and copy them into these devices and then map them and access them directly through, byte addressable means.
Yep.
And so this is, kind of would work in our workflow. And so is this, where you're thinking you're going or, basically these things are so, these production processes where you're producing, these petabyte data sets, they're complicated. You don't just go write them. So you're sort of getting into specific pieces in that pipeline and then maybe, trying to extrapolate or use this technology.
Absolutely. Yeah. Andy described those as persistent memory aware file systems. I think that's a good description, where you use kind of file attributes to set up the access to it, and then you access it directly as a memory read or write if you need to. So we'll see where it goes. A little bit depends on the use case as well. I can't imagine that there are cases where there's a data set where you really just do want to read and write the 6 terabytes directly. Some people know how to do that.
We're doing that today. So, and they're 100 terabyte data sets.
There you go.
I can describe it. And it's, you basically want to chase pointers through these data sets in a parallel fashion over hundreds of servers. And so we're doing that today using mmap, but you're paging it into the block cache and then accessing it. So we want to get rid of the cache and we want to access it down to the page cache and access it down to the cache line.
The mmap part made sense to me. Getting the page cache out of the way is, I think, the objective here. You don't know it, but what you just did is volunteered to be part of this.
I'd be happy to.
I hope so.
Thank you.
Thanks.